Assalamu alaikum. So today we're going to finish off our discussion on Gauss's law, and we're going to look at some interesting applications. We've already started this train of argument. Now suppose we have an infinitely charged sheet, and it's uniformly charged. It's two-dimensional. This means that the charge per unit area is constant. It's homogeneous throughout this metal or conductor. We also know that the electric field due to this conductor is pointing away from the charges, and it's a constant, and it's given by sigma over 2 epsilon naught. If this is my y-axis, then the direction is along the j unit vector, so this is the electric field. Now on the surface of this metal, the electric field is normal to the surface. At all points on the surface, it's normal everywhere. Alright, this is something we know from Gauss's law, because the electric field cannot possibly point in any other direction, because if it did, it then would have two components, a yellow component that is normal and a blue component that is parallel. And if such a blue component did exist, it would cause the movement of charges parallel to the surface. But that's not possible, because it's an electrostatic condition. Everything is in equilibrium. No force should be acting on the charges. This is what equilibrium means. Another way to look at is that there's nothing special with the direction that I've drawn here. I could have equally well drawn an electric field that is pointing in the downward direction. And in this downward direction, the parallel component of the electric field would be downwards. So if I were to draw an upward pointing electric field, I was at equal liberty to point it to a downward pointing field, and they would produce parallel fields in opposite directions. But none of them are special. The up direction is the same as the down direction, because it's an infinitely charged sheet. The expanse of the sheet is infinite. So the only way out of this conundrum is that I cannot have a component parallel to the sheet. Therefore, the only possibility is that the electric field is pointing normal to the surface of this sheet of charge. So this is what happens in a metal plate. Now suppose I have a metallic cylinder, and this is charged. It's a sphere. It's solid. It's not a surface. It's now a volume. And suppose my charge is uniformly distributed on this. Wherever the charge exists on this surface or sphere, it's uniform. But my argument is that charge can only exist on the outer surface of this solid object. And we've already seen a demonstration to this effect. Suppose a charge did exist inside this sphere. If a charge existed, then I could have drawn a Gaussian surface inside this solid object, and this Gaussian surface, since it encloses a charge, the electric field, the electric flux that is coming out of this Gaussian sphere would not be zero. Alright, this is actually disturbing me quite a bit. Okay. Please do come in time to the class. Alright. Suppose I have a sphere, and it's a metal, a conductor. It's solid. First of all, I would argue that if this were a charged object, then all the charge must exist on the outer surface. Suppose my argument was incorrect, that charge indeed existed inside this solid object. Alright. Then what I would propose is that inside this object I take a shell which is a thin layer of solid. Since it's a sphere, and if charge did exist, the charge would symmetrically distribute itself on the shell. Okay? So I am proposing that, alright, let's see whether charge can exist inside this solid object. If it did exist, then the charge would distribute itself equally, symmetrically on this shell. I'm just focusing on this shell. There are other shells as well, but I'm just focusing on one of them. Suppose such a scenario did exist. Alright. Now what I would like to do, I would like to draw a Gaussian surface, which I'm drawing in yellow, that's outside this shell. Since this Gaussian surface now encloses some charge, let's call this amount of charge plus Q inside the shell. There's no charge anywhere else. It's just on this shell, and the amount of this charge is Q. This is something that I'm proposing. Now the total flux phi through this surface, according to Gauss's law, would be Q over epsilon naught. Alright, this is Gauss's law. But this equals E dotted with the local area vector integrated over the yellow surface. Now if such a charge did exist, then its field would be radially outwards because it's a spherical distribution of charge. There is no other direction to which the electric field could point. So the electric field at this Gaussian surface would have pointed radially outward if such a charge indeed existed. Now you take unit normals to this surface, all of them are pointing parallel to the supposed electric field. Therefore, the angle between the local electric field on all points of this yellow Gaussian surface with the local area vectors is going to be 0. Therefore, cosine theta is going to be 1. And this electric field will have the same magnitude because it's concentric with the center of this shell. So what I could do, I could take this E outside this integral. The integral of dA would simply become the area of this Gaussian surface, and this would then equal Q over epsilon naught. But since Q is non-zero, because I have proposed that a charge does exist inside the shell, the electric field will be non-zero. So if there is a charge inside the metallic shell, then there would be an electric field inside the shell. But if there is an electric field inside the shell, since it's a metal, if I have mobile charges here, they are experiencing an electric force because there is an electric field. What this would do is that all the charges that are on the shell here, the hypothetical charges, all of them would be experiencing a force that's outward because there exists a non-zero electric field. But that would mean that the charges are moving. But we have an electrostatic condition in which everything is in equilibrium, so charges cannot move. They cannot experience a force. So the only way out of this conundrum, out of this puzzle, is that our initial assumption is wrong. It's false. Charges cannot exist inside the interior of this shell. Because if they did exist, then there would be an electric field inside the metal. And if there were an electric field inside the metal, the charges would be experiencing a force. But we have electrostatic conditions. There is no current flowing through the material. Everything is in equilibrium. So charges cannot exist in the interior of a metal. If a metal were to become charged, like the dome of a Van de Graaff generator, all the charges would reside on the outer periphery of the object. So if this were my metallic sphere, then all the charges would exist. If it were a positively charged object, all of them would exist on the outer periphery, on the outer surface, on the skin of this sphere, and no charge would exist inside. So if this were a metallic object that were charged with an amount Q, all of that Q will equally distribute itself on the surface of the sphere. Since it's a sphere, it's a uniform sphere, the only way the charge can puddle up or distribute itself on the surface is uniformly. So it's going to uniformly distribute itself on the surface of the sphere. Now what we would like to know is what's the electric field that is produced by this charge distribution. Okay? Because a point charge produces an electric field. So this charge distribution that's on the outer periphery of the surface would also produce an electric field. Remember that in this scenario, if I were to draw a Gaussian surface inside the sphere, the flux through this surface is going to be zero because there's no charge inside. The flux is zero, and in this particular case, the electric field is also zero. Alright? Remember that if I draw a Gaussian surface and the flux through this surface is zero, the only point that I can make is that the charge inside is zero. There could be charges outside, by the way, and still produce a zero flux through the surface, because if I have a positive charge like this, it will produce a non-zero flux through this surface. And the electric field will exist at this point as well as this point as well as at all other points inside this surface. But the flux through the surface is zero. So zero flux does not necessarily mean zero charge. But in this case, zero flux does mean charge because it's sphere. And the only way that the charge can distribute itself is in a spherically symmetric fashion. And by this argument, I've shown that for the electric field to be zero inside this metal, all the charges must exist on the outer periphery. So if I drew a Gaussian surface inside this metallic sphere, no flux would pass through it and it will not enclose any charge. I can draw a Gaussian surface as big as I like, unless I'm up to the point that I'm within the volume of this solid. So I can make a Gaussian surface right at the surface, but just below it, just barely touching the surface. And my argument will still hold that the charge inside this Gaussian surface that is just barely skirting the surface of the sphere is zero. Alright? Now my next question is that if I have a charge that is distributed on the surface of a sphere, is uniformly distributed, what's the electric field produced due to this charged object? Right? Because there are charges, they will produce an electric field. The electric field inside is going to be zero. But what's the electric field outside? So if this is a sphere, a uniform sphere, a metal or a conductor, and all the charge is on the outer periphery, it's just on the skin. No charge inside. No net charge inside. Now I would like to draw the electric field due to this charge distribution. Now one point is, alright, first of all I draw a Gaussian surface, which is another sphere that is concentric with this sphere. Now this charge is spherically symmetrically distributed. So the charge distribution is spherically symmetric. Which means that this charge, whatever it is, of magnitude capital Q, distribute itself in a perfectly homogeneous way on the surface of the sphere. Now, the point is that if I take any point here and if I were to draw the direction of the electric field, the only possible and meaningful direction in which that field can point is radially outwards. By the same arguments that we've already been using, because if the field were to point in any other direction that is non-radial, it will have two components, one that is radially outward and one that is tangential to the surface. Tangential means something that is parallel to the surface at this point. It's a tangent to the surface. If I draw a sphere, I can draw a tangential plane, a line that is tangent to the surface. So if the field were pointing in this direction, this would have a tangential component and a normal component. But this tangential component, there's nothing special with this direction. It's a sphere. So this tangential component could be pointing downward. It could be pointing anywhere. All the directions stand on an equal footing. So there's nothing special with this direction. Therefore, the only way out of this puzzle is that this component cannot exist. The electric field can only point in the outward direction, in the radially outward direction. So at all points on the surface, on this Gaussian surface, the electric field is going to be of the same magnitude, because there's no reason why the electric field here will have a different magnitude than the electric field here, because this charge is spherically symmetric. There's no reason why the electric field here has to be different from the electric field here. If you're equidistant from the center of this sphere, then the electric field's magnitude is going to be the same at all of these points. There's no reason why the field will change from point to point. Okay, do you understand? And the reason is that this charge is spherically symmetrically distributed. So now the electric field is the same everywhere, and it's pointing in the radial direction, so we can use Gauss's law to find out what the electric field is. The electric field E dotted with dA integrated over this Gaussian surface is simply the electric field into 4 pi r squared, where r is this distance here, and this equals the total charge enclosed by this Gaussian surface, which again is capital Q divided by epsilon naught. So this is Gauss's law, and now we have the special case in which we can use Gauss's law to find the electric field, because of the spherical symmetry of the charge distribution. So the electric field at all of these points, E, P, can be found out as Q over 4 pi epsilon naught r squared. Right? Now if I shrink this Gaussian surface, the Gaussian surface is a figment of my imagination. It doesn't really exist. So it's there because I would like to apply Gauss's law. Now if I shrink this Gaussian surface and make it smaller and smaller, so that at one point I'm just barely outside the surface of the sphere. Once again the electric field has to point normally outward, it has to be radially outwards, alright? So on the surface of the sphere itself, if I were to find out the direction of the electric field, it's going to be radially outward. So on the surface of the sphere itself, which is a Gaussian surface which just skims the surface, just on the outer periphery of the surface, the electric field once again has to be normal to the surface, which means the electric field has to be radially outwards. And what does radially outward means? Radially outward means that at all points on the surface of this object, the electric field is normal to the surface. So on a metallic sphere, the electric field produced by a spherical distribution of charges on the surface is normally outwards. What if I have a metal that is not a sphere? Suppose I have a pear-shaped metal that is standing on an insulating frame, and this is a metal, a conductor, and it's charged. It carries a charge capital Q on it. So by the same argument, all of that charge must exist on the outer periphery. But in this case, since the medium is not uniform, it's not a nice spherically symmetric object, it's a mango shape. Therefore, the charge will not equally distribute itself on the surface. However, since the electric field has to be zero inside, on the surface, if I take any point on the surface, any small patch, the electric field is going to point normally to the surface. It's going to be pointing normally outwards to the surface. Here the electric field is going to point in this direction. Here the electric field is going to point in this direction. here it's going to point in this direction, and so on. So at all points on the surface of this object, the electric field is going to point normally outwards. Because if it did not point normally outwards, if this were the hypothetical direction, I could resolve it into its two components, one that is normal and the other that is tangential or along the surface. But a component along the surface will cause the charges to accelerate. The charges will no longer be in equilibrium. So if you want everything to be in equilibrium, the only possibility is that the electric field is normal to the surface. Alright? And the electric field that comes out from a charged metallic object is given by sigma over epsilon naught and pointing in a unit direction that is unit normal to the surface. And why don't we have a factor of 2 here? Here, if you observe, we have a factor of 2 over epsilon naught. But here, I have not put in this factor of 2 epsilon naught. Why is that? That's not the reason. Here, for an infinitely charged sheet, I put in a factor of 2. This is something we derived from Gauss's law. Here, this electric field is given by the charge density at this point divided by epsilon naught, and the direction is unit normal. So at all of these points, the electric field is pointing in different directions. Number 1. Will the charge density be the same on the surface? No. The charge density can vary from point to point. So here the charge density will be different, here it will be different. If I make a sharp protrusion, something that's sharp here, the charge density will in fact be quite high here. This is something we'll learn when we talk about potential. Something that is smooth, the charge density will be lower. So at sharp edges, at pointed edges, there will be more charge per unit area. So the charge density is not uniform. But at each point, the electric field is given by the charge density at that point divided by epsilon naught, and this is the local direction of the electric field. But I don't have a factor of 2 here. Can you come up with the reason? This is a closed surface, but that's not necessarily the reason. Exactly, because there is no electric field inside. Inside this material, the electric field is 0. So at the surface, the discontinuity of the electric field is sigma over epsilon naught. Right? So there is no electric field inside, but there is electric field outside. Here there is an electric field to the left and there is an electric field to the right. So the discontinuity in electric field is from minus sigma over epsilon naught to plus sigma over epsilon naught. Alright? So it goes from negative to positive. Here it goes from 0 to positive. Alright? Now, alright, so this is the electric field due to a conductor. It's always pointing normal to the surface of the conductor. Now let's look at another example. Suppose I have a sphere, but now that sphere is really composed of 2 kinds of rings, 2 kinds of hemispheres. Okay? So I have a top hemisphere and I have a bottom hemisphere. And they are glued together by some insulator so that they don't make a connection. So there is some insulator here, so that charges cannot flow from the top hemisphere to the bottom hemisphere. Right? Suppose I have this configuration. Now what I propose is that on the top surface the charge density is sigma 1 and on the bottom surface it's sigma 2. And they're not the same. So now I have, if this is larger, I have more charges per unit area on the top hemisphere. and I have fewer charges per unit area on the bottom hemisphere. Alright, I'll come to this point, but I think there are a few confused faces. Let me derive this electric field here. How do I derive this electric field? I can just draw a Gaussian surface, which is a cylinder, whose one end penetrates inside the interior of this object. And these sides are normal to the surface. And this end cap has area capital A. Now I know by construction that the electric field inside has to be zero. So the electric field that exists, it's normal to the surface, so the dot product with the areas on the curved surface is zero, and the only contribution comes from the end cap. So this contribution gives me a flux of E times the area A, but this just equals the charge enclosed. The charge enclosed is sigma, where the sigma is the charge density here, into A, which gives me the total charge divided by epsilon naught. So my electric field is sigma over epsilon naught. So I can use Gauss's surface to find out the electric field on the surface of the metal. It's sigma over epsilon naught. Alright? In this particular case, it's sigma over 2 epsilon naught. It's half of this value, because the electric field is extending to both sides. Here the electric field is zero inside, it's like a step function, and it's non-zero outside. Now consider this case in which I have a non-uniform charge distribution. It's spherically symmetric only in the top hemisphere and spherically symmetric in the bottom hemisphere, but overall it's not spherically symmetric. So in this case, can I apply Gauss's law? By the way, I can always apply Gauss's law. Gauss's law does not fail us. It's always applicable. So I can draw a Gaussian surface, and the flux through this surface is again going to be the total charge enclosed over epsilon naught. Now the total charge enclosed is sigma 1 into half of this surface area, 4 pi r squared divided by 2, which is 2 pi. If this radius is small a, 2 pi a squared plus sigma 2 into 2 pi a squared. So this is the total flux that is coming out of this surface. Gauss's law is still applicable, but I cannot use Gauss's law to find out the electric field. The reason is that the electric field, say at this point, of course it's going to be larger than the electric field here, because here it's in close proximity to a higher density of charges. Correct? And here it's in close proximity to a lower density of charges. So the electric field that a test charge would see here is much higher than the electric field seen by a test charge here, because there are a higher propensity of positive charges which are densely packed in the vicinity of this point. So the electric field here is not going to be the same as the electric field here. So I cannot bring the electric field out of the integral of the left hand side of the Gauss's law, and I can make an easy electric field calculation. Alright? So applying Gauss's law will not be straightforward in this case. However, Gauss's law is still valid. You can use it to find out the flux through a closed surface. So this flux is independent of what the geometry of these charges are. I can make this surface into some squished kind of object which carries the same amount of total charge Q, and still the flux through this surface is going to remain unchanged, because the flux only counts the number of charges or the amount of charge inside. But calculating the electric field from Gauss's law requires a certain conception of the symmetry of the problem. Alright. Yes. For each hemisphere? No. Because if I just consider this hemisphere, and I would like to calculate the electric field at this point, I can of course use Coulomb's law. But at this point the electric field is going to be different from the electric field here, it's going to be different from the electric field here. Alright? So it's not going to be straightforward using Gauss's law here to calculate the electric field. One more question, yes. Well, this is just the total charge density into the surface area. 4 pi r square is the surface of the sphere. So I half it because it's a hemisphere. ठीक है? एक मिनट पानी खामोशी भी अच्छी होती है. Now what we've done here is we've seen the electric field produced by a spherically symmetric distribution of charges. Now let's see what happens when we have a uniform electric field. And we place a charged metallic object inside this. Or okay, let's suppose that our metallic object is uncharged, okay? It does not carry any net charge, so it's placed inside this electric field. So I just have a metallic object and I plunge it into this uniform electric field. Why is this uniform? Because the electric field streamlines, they are equally spaced. Okay, this is a uniform field. Now what's going to happen is that if I look, apparently what's happening here is that the unit normal to the sphere is pointing in this direction, but the electric field is not along the normal, it's pointing in this direction on the surface. So they're not parallel. Here we would like all the electric fields to be parallel to this surface, to the unit normals, that is normal to the surfaces. Likewise, here the electric field is pointing in this direction, but the unit normal is pointing in some other direction. So this of course will not satisfy our condition that the electric field inside this volume is zero. Because here the electric field will have two components. It will have a component that is along the tangent and a component that is pointing inwards. This component, now this component that is parallel to the surface will cause charges to flow. But we would like a condition of equilibrium. So what's going to happen is that the electric field lines will change their orientation in such a way that they remain normal to the surface. So if I draw the electric field pattern for an uncharged object that is placed inside a uniform electric field, here the electric field is going to remain straight, but close to the surface, here it's going to be of course straight because here it's still normal to the surface, but the electric field lines here are going to tilt, so that at the point of intersection with the metallic object, they're going to be normal to the surface. So that this electric field line is going to be like this. Here there's an electric field that is going to change its course slightly. Here the electric field is going to shift downwards. Here it's going to shift downwards. Here it's going to tilt slightly in this direction. Here the electric field is normal. It goes like this here, like this, and far away from the metallic object, the field becomes uniform again. So this is the new pattern of the electric field in equilibrium condition. And what this really means is that the electric field inside, the net electric field inside is zero. And if this was an uncharged object, the electric field lines that are coming from the outside, they have to stop somewhere. So what happens is that positive charges accrue on this side, they collect on this side, and negative charges collect or accrue on this side. Alright, and why is the electric field inside zero? Because how does it come about? Sorry, there are I'm so sorry. There are negative charges here and positive charges. I'm so sorry about that. So there are positive charges that accrue here and negative charges that collect here. Because electric field lines emanate or come out of positive charges and they sink into negative charges. So why is the net electric field inside zero? The net electric field inside is zero because the externally imposed electric field is pointing in this direction. This is the externally applied field, Ext. But this new distribution of charges creates an internal electric field, E internal. Because there are positive charges here and negative charges here, they will produce an electric field of their own. And everything readjusts in a neat fashion in a way that this external electric field is the same magnitude as this internally electric field, which is called a dipolar field. So that the net electric field inside remains zero. In all of these cases, once again Gauss's law is applicable. If you draw a Gaussian cylinder that is normal to the surface, the electric field inside has to be zero. And the electric field outside has to be normal to the surface. Once again. So the electric field lines will redistribute themselves and the charges will redistribute themselves in such a way that the total charge in this object is still zero. The amount of negative charge here is equal to the amount of positive charge here. In other words, this region picks up all the mobile electrons. The mobile electrons just gather together and curl up on this side, and here is a depletion of mobile electrons. This region is devoid of mobile electrons, so it gets a positive charge. Overall, this sphere still remains positive, neutral. It has no path for the charges to come in or out. But this redistribution of charge must take place if the electric field lines have to readjust so that they are always normal to the surface. G.
So when you place an uncharged sphere inside the electric field, will it initially the electric field lines pass through the sphere or they extend?
Exactly, that's a very good question. Suppose I have this uniform electric field and my friend has asked a very nice question is, now we have a metal object, it's uncharged, there is no distribution of charges, right? It's just mixed together, smeared up like a soup. There is no difference, there is no dipole here. Here we have a dipole. So when we place that object inside this electric field, what happens all of a sudden? The charges must redistribute themselves. Initially, yes, there does exist an electric field inside the interior of the surface. And it causes the electrons to accelerate and distribute themselves in such a way that a new distribution is created over some length of time, which could be of the order of picoseconds to nanoseconds. This is the transient stage. But once equilibrium is established, this transient state is over. The distribution of charges has taken place in such a way that the net electric field goes to zero. So initially, yes, there will be a transient electric field that will cause the charges to redistribute. The charges need some force to redistribute, and that force is given by some initial electric field that just appears at the time when this sphere is plunged into the uniform field. Yes, one question. No, after it has rearranged and equilibrium has been established, the electric field inside is zero. Alright, now one very nice example. It's a holistic problem, a nice application of Gauss's law. And I received an email from a student who was confused about volume, charge, density, etc. G. Again, the charges will redistribute themselves for whenever you change an electric field, a transient state occurs, and it will take some finite amount of time for the electric field to appear. Now, I have a question. Now, this nice question brings me to a nice idea. Suppose I have an electron and I am at a distance x from the electron. This is point P. Now, is there an electric field at point P? Yes, there is an electric field. That electric field is pointing in this direction. Now suppose I have a gun that can fire positrons, which are antiparticles to the electron. Now a positron has the same mass as an electron, but it's positively charged. Now I have a positron gun and I fire a single positron onto this electron. So here comes in a positron, and what the positron does is that you've taken a course in modern physics, what does it do? It's going to annihilate the electron. So this pair is annihilated. This process is called pair annihilation. And it will produce two photons, uncharged particles, that beam out in different directions. Two photons. Now this process is called pair annihilation. Once pair annihilation has taken place, the charge here is zero. Alright? So what's the electric field at point P when pair annihilation has taken place? It's going to be zero. Suppose pair annihilation takes place at time equals to 0. Now before this time there existed an electric field, and if I were to plot the magnitude of the electric field, there's some magnitude. Once annihilation takes place, the charge distribution changes. The electric field would also change. But would the electric field change instantaneously? Yes? So I have an observer here, I have a test charge here. As soon, and I'm holding it with my hand, but I can feel the force on this charge. Suppose at time t equals 0 annihilation has taken place. The force has to go to 0. Will it go to 0 at time t equals 0? It's going to take some amount of time. There is no such thing as action at a distance in physics. The effect of this redistributed charge is going to propagate with the speed of light. So after a time x divided by c, where x is this distance, will the electric field diminish to 0. And in between, you do not see any change in the electric field. So it takes a finite amount of time for the electric field to go to 0, for the presence of a new electric field to be felt. This phenomenon is called retardation. Retarded fields. It's not the same as the retardation you study in mechanics. So charge redistribution might take place, but the new electric field is established after a certain delay. ये इसी तरह कि भाई ये एक इंफॉर्मेशन आई कि ये इलेक्ट्रॉन पॉजिट्रॉन्स ने एनाइलेट कर दिया, चार्ज बदल गया, तो उस इंफॉर्मेशन को पहुंचते तक इस ऑब्जर्वर तक कोई कासिद चाहिए, कोई पैगामबर चाहिए, किसी ने पैगाम लेके जाना, उस इंफॉर्मेशन की ट्रैवल में कुछ वक्त लग रहा है. ठीक है? So this is retardation. Now the example that I would like to highlight and the system that I would like to propose is slightly complicated. Suppose I have a sphere that carries a charge plus q, and it's an insulator, not a conductor. So charge can reside inside the insulator, which means that there can be an electric field inside the insulator. But that does not cause the charges to accelerate, because there are no mobile electrons, there are no free carriers in the insulator. So strong electric fields can exist inside an insulator. Alright? Because there are no mobile charge carriers. So an insulator is vividly different from a conductor. Suppose the charge Q is in the entire volume of this insulator. So when I have charge distributed in a volume, I would like to talk about the volume charge density, rho. Now if the radius of this sphere is small a, the volume charge density is going to be the total charge divided by the volume, 4 over 3 pi a cube. So this is how I would define the charge density. And I suppose that this charge density is uniform. This means that the charge is homogeneously distributed inside the solid. It means that if I do a surgery and take a small volume outside this insulator, volume V1, and calculate the charge on it, then I put the volume back, and then do another surgery and take out another piece of the same volume from another location inside this cylinder, and I find out the charge on it, it's still going to be the same. This is what is meant by homogeneous or uniform distribution of charge. And of course it's spherically symmetric because it's a sphere. There's no reason why charge will accumulate in one end as compared to the other. It's a homogeneous isotropic material. So in isotropic materials which are homogeneous, there is no reason why a charge will not be uniformly distributed. Alright? So this is an insulator. So I'm building up your basics here. This is a lot of conceptualization or visualization that goes into understanding of these problems. Now what I have is something rather strange. Outside this insulating sphere, I have a ring. Alright? Now this is a metallic ring. It has an inner radius of B and an outer radius of C. In between A and B there is void, there is nothing, it's just vacuum. So this region that's in between is generally called an annulus or an annular region, right? This is an annulus, it's void, there's vacuum here. This is a metal, inside we have an insulator. Alright? Now this ring has some thickness. It's not a shell, it has some thickness because B is not the same as C. It's a metal. Suppose this metal carries a total charge of minus 2Q. It's negatively charged. Alright? Now what I would like you to do, and we'll do it together, is we would like to find out the electric field here, 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 inside this insulator, inside the annular region, inside the outer shell, and outside the entire geometry. We would like to find out what the electric field looks like and what is its magnitude as we go from the center of this system to infinity. What's the electric field going to look like? And we're going to plot this electric field. Alright? So we break up this problem into smaller components. First of all, we would like to find out the electric field inside this insulator. First of all, we know that the charge is uniformly distributed, so it must be spherically symmetric. So I would like to draw a Gaussian surface inside this interior volume, inside the insulator. What would that surface look like? Gaussian surface बनाना चाह रहा हूँ एक sphere draw करूँ जिसका center of the system हो. So I would like to draw a Gaussian surface that has this point as its center. Okay, and this surface has a radius r. Now if I were to draw the electric field, I need to know what the direction of the electric field is, what's the direction and what's the magnitude. Now on all points on the surface of this Gaussian surface, the electric field will have the same magnitude because there's no other reason why it has to be different. Okay? And it's always going to be pointing normally outwards because it's a spherically symmetric charge distribution. It cannot point in any other direction because any tangential direction is the same as any other tangential direction. So only the radial direction is unique. Okay? So on the surface of this Gaussian sphere that I've drawn, I can apply Gauss's law to determine the electric field. So for R smaller than A, that is, I'm inside the insulator, the electric field into dA integrated gives me 4 pi r squared, right? Equals the charge enclosed inside this Gaussian surface. Now what's the charge enclosed? Q, not Q, it's going to be the charge density into the volume of this Gaussian surface, which is 4 over 3 pi r cube or a cube? R. It has to be r cube, not a cube, because we have drawn a Gaussian surface inside the insulator and its volume is 4 over 3 pi r cube. There is charge outside this Gaussian surface as well. So we don't have to take that into account. Only the charge that resides inside this Gaussian surface. 4 over 3 pi r cube over epsilon naught. Which means that the electric field is rho r 3 epsilon naught. Nice. So what's going to happen is, now I would like to plot the electric field versus the distance from the origin. This is 0, this is point A. Could you please plot what the electric field is going to look like? The magnitude is going to look like a straight line. It's going to be a straight line. So this straight line starts from 0 and it goes up to r equals A. At this point the electric field is rho A over 3 epsilon naught, right? This point is rho A over 3 epsilon naught. So it's going to increase linearly. Inside the insulator, the electric field is not 0. It's going to ramp up from 0 to a maximum value at the radius. Alright? Yes?
So if we take an integral of this value from 0 to A, then that will be the total electric field comes out of the...
What do you mean by there is no such thing as total electric field? It's a question that has an answer that explains the concept. There is no such thing as a total. You cannot integrate from one point. That will give you the total flux. There is no such thing as the total electric field. The electric field is a local concept. It varies from point to point to point. You cannot add the electric field at 2 points. It doesn't make sense. Okay? So this is the electric field inside the insulator at a radius r. Yes?
So we cannot apply this formula without applying Gauss's law?
Yeah, you can use Coulomb's law, but it's going to be very complicated.
Sir, no, I mean, sir, अगर हम inner sphere को consider नहीं करते,
अगर ये है ही नहीं है,
अगर sir inner sphere जो हमने Gauss's law के through,
ये वाला Gaussian surface,
अगर हम इसको consider नहीं करते, तो हम formula apply नहीं कर सकते।
नहीं, हमें जरूर कोई ना कोई Gaussian surface बनानी पड़ेगी, क्योंकि we would like to find a flux to that Gaussian surface, वो बनानी पड़ेगी, उसके बगैर चारा नहीं है।
सर अगर हम sphere को symmetry consider करें,
तो वो total flux through वो फिर electric field at this point दे देगा, but you would like to find out the electric field at varying r. Alright? Now we would like to move into the annular region. Okay? So in the annular region, we would like to draw another Gaussian surface. Once again, we draw a Gaussian surface which is a sphere that goes through the annular region. Here again, the electric field. Now there is a cornucopia of colors here. I don't know if you can really figure out what's going on. There's so many colors here. But if you draw the electric field at all of these points on the sphere, they're going to point normally, radially outwards, and they're going to have the same magnitude. Because there is no other way in which the electric field can exist in this case, because of the spherical symmetry of this scenario. So for R that is greater than A and it is smaller than B, so we're inside the annular region, we would again apply Gauss's law, E into 4 pi r square. Now r is the distance from the origin, divide equals 1 over epsilon naught, the total charge enclosed. Now what's the total charge enclosed? It's capital Q. But capital Q is just rho times 4 over 3 pi A cube. Now I have the total volume of this insulating sphere, because all of it is inside the Gaussian surface. Now I can cancel out the 4, the pi, and E turns out to be rho over 3 epsilon naught A cube over r squared. So this is the annular region. In your notebooks, could you please go through the exercise of plotting what this electric field is going to look like in the annular region? Pehle karo. A तक क्यों 1/r square मीटर बना के दिखाएं। उसके आगे देखो A तक लीनियर है, आगे A और B के तरफ पूरा बना। The electric field is in, but the insulator is a charged object. It will produce an electric field outside. Because now the total charge enclosed is within the entire volume of the insulator, and that is a volume 403 pi A cube. That's the left hand side of the Gauss's law. गुड काम तक जाए किसी पॉइंट पे आके रुक जाएगी, ठीक है। जीरो पे क्यों पे आके रुक जाएगी, राइट। इंक्रीज हो रहा है 1/r आज बढ़ रहा है। Hello. Good. Good. Hello. Hello. All right. So you figured out this problem. Hello. ठीक है। Alright, so the electric field is just going to fall inverse quadratically, just like Coulomb's law, right? 1/r square dependent. It's as if all the charge is at the center, right? Because of spherical symmetry, we can assume that all the charge is at the center. So it's going to fall off quadratically, like the Coulomb's law. It will continue falling off. If we did not have the outer conductor, it will continue falling off. But then it stops at B. Alright? Now when it stops at B, something strange happens. Now I would like to redraw that figure with less clutter, with less multitude of colors so that you can understand what's going on. So you have an insulating sphere and you have an outer conducting ring. There is some electric field inside, some electric field outside. This carries a total charge of plus Q. The electric field outside, if I were to draw the flux lines, they would look like this. Just like a point charge, the intensity of the electric field, the strength of the electric field is smaller as we go away from the insulating sphere, and that is demonstrated by the 1/r² dependence. The field lines are further apart away from the insulator, but they're all pointing radially outwards. So all of a sudden what happens is that inside this conductor, the electric field has to be zero because of Gauss's law. In equilibrium, there can be no electric field inside the metal. So in the interior of this metal, the electric field has to be zero. Now this necessarily means that the electric field that just touches the surface, the inner periphery of this metal has to be normal to this surface. And since it's a radial situation, it is indeed normal. And the electric field inside has to be zero. And if the electric field inside has to be zero, this really means that if I were to draw a Gaussian surface inside the interior of this metal, which I've drawn in pink here, the total flux through this Gaussian surface has to be zero. Alright? Because the electric field is zero at all of these points. So if the electric field is zero at all of these points, the flux has to be zero. Remember, Gauss's law does not work two ways. If the flux is zero, it does not mean that the electric field is zero. But if the electric field is zero at all of these points, then the flux has to be zero. Because the flux is simply E dotted with dA. Now if inside the metal, the electric field here is zero, here it's zero, here it's zero, here it's zero, everywhere it's zero, then I take the local dot products and add all of them up, the flux has to be zero. But then this equals the charge enclosed divided by epsilon naught. This means that the total charge enclosed by this pink Gaussian surface has to be zero. But what I observe here is that the insulator carries a charge plus Q. And if I were to make the total charge enclosed zero, then there has to be some additional charge that exists on the surface of this metal to make the net charge inside this pink Gaussian surface zero. And what's that charge going to be? It's going to be minus Q. So there must exist a negative charge of total magnitude minus Q on the inner periphery of this object. So there is a negative charge here. So this surface bears a negative charge minus Q. So that the total charge enclosed by the Gaussian pink surface is zero. There's plus Q on side in the insulator and minus Q on the inner periphery of the metal ring. Only this charge distribution will ensure that the electric field inside the interior of this metal is zero. See how the charge redistributes itself. So if I were to ask you the charge density on the inner surface of the metal, what would that charge density be? I'm not talking about volume density, surface density. That charge density is going to be minus Q over 4 pi B squared, which is the total surface area of the inner surface of the metallic ring. So a charge this charge density develops on the inner surface, and inside the interior of this metal, the electric field is zero. So if I go from B to C, the electric field has to be zero. So at the point B, all of a sudden, the electric field drops to zero and then remains zero up to the point C. Nice. That's quite nice, in fact. Because here what you observe is that there is a discontinuity in the electric field. the electric field suddenly changes. So this discontinuity in the electric field actually tells us that there is some surface charge that exists here. All right? Now what's going to happen outside the entire system? I can draw a Gaussian surface outside the entire system. Now this Gaussian surface is at a distance r from the center. Now what I would like to do is I would like to find out the electric field at r greater than c. Once again I know that if an electric field existed, it would be pointing radially outward and it will have the same magnitude on the surface of the sphere. So once again Gauss's law comes to my rescue and I can apply Gauss's law with quite facility. So E times 4 pi r square would now equal 1 over epsilon naught, the total charge enclosed. Now what's the total charge enclosed by this outer Gaussian surface? It's going to be plus q minus 2q, which is going to be minus q. Because the total charge on the outer metal is minus 2q. And out of this minus 2q, minus q has appeared on the inner surface. So there is a residue charge of minus q. Out of this total minus 2q, minus q has appeared on this surface. So you still need another minus q, and that minus q will go on the outer surface to make the total charge on this metallic ring minus 2q. So outside this surface, the total charge enclosed is plus q on the insulator and minus 2q on the conductor. It's minus q. So this becomes minus q over epsilon naught 4 pi r squared. This is the electric field outside the metallic ring. And if I were to plot this electric field on this graph, all of a sudden the electric field changes its direction. From a positive side, it acquires a negative sign. So it will jump in the downward direction. There's another discontinuity. And then it's going to decrease quadratically with 1 over r squared. So it's going to decrease like this. Beautiful. Once again there's a discontinuity here. And mind you, there's a discontinuity because on the outer surface of this metal ring, this surface, there is a surface charge. What's the amount of that surface charge? Minus q. Because there's minus q on the inner surface, there has to be minus q on the outer surface. On this surface. So that the total net charge on the metallic ring is minus 2q. So there's a charge minus q here. Even though the charge density on the outer surface will be smaller because the radius is larger. So this is a plot of the electric field, and you can see discontinuities inside the electric field, and these discontinuities appear whenever there is a sheet or a surface of charge that comes in the middle. Right? Now I have time for one question. In the next lecture we're going to start our discussion on electric potential. There's going to be a quiz on Friday, but before you leave I would like to take a question. Yes? At radius C? Outside C? Alright, what's the direction of the electric field outside the radius C? Outside C, beyond C. It's going to be inwards. Okay? So the electric field outside the surface is going to point in this direction. Okay? So with the negative sign. Alright, thank you very much. Thanks a lot.